All right, so Sophie already did a great job of introducing me, but I'm Dave Lucia. If you don't know me, I am a CTO at a company called Bitfo. Find me at DavyDog187 on Twitter. So this is my third Code Beam, and I'm super excited to be here in person. It's been about 2 years since I've last been at Code Beam, and I missed seeing everyone in person. It's been really great today to see so many faces. So since the last Code Beam, March of 2020, a lot has changed for me personally. I added a new dog, a new Pomeranian to the mix. I have an almost 2-year-old son, and I have another one on the way in early April. Thank you. So we're not going to talk about my dogs and babies today. We're going to talk about time series. So what I want to get into is what is time series data and why might you care about it. We're going to talk about TimescaleDB specifically, a database that I use at my work. And then we're going to introduce the Timescale library for Elixir, which I've been working on. All right, so let's get into the meat of it. What is time series data, and what makes working with it unique? So first of all, time series is everywhere. You could think of application metrics, CPU utilization over time, memory utilization over time, financial data like prices changing, volume, eventing applications where it's producing things in response to human interaction or whatever it may be, business intelligence, Internet of Things. There is time series in all of this. But let's get into more specific examples so that we could really understand what I'm talking about. So let's use the example of a fitness tracker, a heartbeat. So here we see, going back in time, we see heartbeats. And these heartbeats occur at a point in time, and they belong to a person. Now, from these events, we can aggregate information and find new summaries of information. So for example, if we want to calculate the beats per minute of your heartbeat, we would just count up in a 1-minute window the number of heartbeats. And you can see if there's less heartbeats, your heartbeat is actually slowing. The rate at which your heart is beating is slowing. So in our heartbeat example, and for any time series example, there's 3 properties that really make time series data unique. One is that it's always appending data, so you're never adding data to the middle or the end. It's always, only adding to the end. You're not adding to the beginning. The other bit is that it's time-centric, so there's always a time component. And the third is that it doesn't change. Once an event has been created in a time series, it's typically immutable. So with this becomes unique challenges that we need to deal with when we're producing data over time. So the first thing is a large number of rows, or just a large amount of data. If I'm producing an event, my heartbeat is beating maybe at 60 beats per minute if I was sitting down watching a talk. Now that I'm giving a talk, it's probably more like 120, 140 beats per minute. And that, if I'm calculating or tracking every single one of those heartbeats, it's going to produce a lot of data over time. Also, the older data gets less valuable. So I probably don't really care about what happened, my heart rate last year, 5 years ago. I might care about, some statistics about, in general, what happened with the change in my heart rate for my general health, but I don't care about the specific beats on some random Tuesday. Sorry, and to query time series data becomes a little bit more challenging because you have to do aggregations over time, which is a little bit different than when you're querying things based on primary keys and foreign keys. And yeah, timestamps are typically what you're dealing with instead of primary keys. So in order to solve the large number of rows, we need a solution for data compression so that we can shrink down the size of data that we're storing. Otherwise, we could end up with terabytes, petabytes of data. We need data retention policies. We don't really necessarily care about older data. We might care about the summary, but we don't want to keep holding data around that we don't need anymore. And in order to query time series data, we need a rich feature set for aggregation. Now, another important thing is that time series doesn't live in a silo. So when my heart is beating, it belongs to me. If I'm building an app around tracking heartbeats, there's going to be other users who are going to be tracking their heartbeats. They might have workouts. They might have goals, preferences, friends. And so if we're ever building applications that work with time series, you don't want to store your time series in one place and all of your relational data in another. They kind of all fit together as one piece. So to continue this example, in the last 2 years, I spent a lot of time sitting inside in front of my computer, and I've been trying to spend the last year focusing more on health and getting back in shape. And with that, I've got my Whoop here, which is my fitness tracker. It tracks things like my heartbeat and many other bodily functions. So let's use this example as we go through and take a look at time series data. So just a quick recap. You might have a device like I have a Whoop. You might have an Apple Watch or a Fitbit. Heartbeats are what we care about today, but you might have skin temperature, blood oxygen levels. All of these things can be treated as time series. All right, so let's introduce TimescaleDB, which is a way to integrate time series data into your product or application. So with Timescale, you're going to get all of the power of regular Postgres, and you're going to get added superpowers for time series data, things that you can't just do with regular SQL, out-of-the-box Postgres. And it's going to give you extensions to standard SQL that make it easier to do certain types of operations on time series data. Now, I really like this quote. This is from Parker and Shannon of Open fame. In a recent blog post, they said, Postgres' killer feature is that it is probably already in your application. And that ubiquity means that if you're building something, new infrastructure is always going to get in the way of releasing product. But if you can work with the tools that you're already familiar with and already comfortable with, that's going to give you a competitive advantage. So with that being said, what is Timescale specifically? It is a Postgres extension. You take your regular Postgres instance, you bring in their code, you add the extension. It provides licenses, an Apache 2 license and a Community Edition license so that you can run Timescale for free in a data center and manage it yourself if you want. They have a cloud offering, which is a paid offering that they'll host Timescale for you and take care of a lot of management and what else. There's an open source repo that has all of the code for Timescale, so it's completely open source. And I'm not being paid to give this talk, but I just want to say they have an amazing support team. I've been using Timescale in production for about 6 months now, and I haven't had an issue that they didn't jump right on and not just help me fix right away, but also educate me on why it occurred and how I could prevent further issues. So getting Timescale up and running is pretty easy on Mac OS. It's a matter of getting Postgres installed with Homebrew, adding Timescale as another brew installation, running 2 scripts, and boom, you're ready to go. All right, so let's get into the meat of it. I've talked about Timescale. It's a time series database. What can it do for me? So the first thing you have to understand is that Timescale is going to take your regular tables, and it's going to upgrade them to add new features. And in Timescale, we call this a hypertable. So we'll see how you build that in a second. But what it does is it takes all of the rows in your table, and it's going to group them into chunks. And it's going to segment these chunks by time. And from this, we get a whole host of features that allow some really powerful optimizations. All right, so here you're seeing some code that I'm sure is pretty hard to read from the back, but when you're going to start working with Timescale, you'll have your ecto migration, and here we're working with Elixir, and you're just going to call a create TimescaleDB extension, and that's going to get everything up and running. From there, in our example, we're going to create a users table, and we could just have a full name for now, and we'll put a unique index on that. And then we're going to create our heartbeats table down at the bottom. And that heartbeats table, it's going to have no primary key, but it's going to have a timestamp, and it's going to have a foreign key to the user that it belongs to. And last but not least, we're going to call create hypertable on that heartbeats table, and pointing to the timestamp column as the time-oriented column on the hypertable. All right, so now that we have our table, let's understand what chunks are. So chunks have time-range constraints. So they're going to have a start time and an end time. And all of the rows, any event that you're generated is going to be automatically put into a chunk based on that time range. So for example, each day's worth of data could be grouped into a chunk. And know that this is all completely configurable within Timescale on a per table basis. Chunks can also be space partitioned. So if you're generating data by time and user, you can have each chunk for each individual user. And this is going to be based on the write patterns of your application. With this architecture, with this chunk architecture, this actually makes it really interesting for building applications that might have a lot of data that you need to distribute across a number of rows. And so these chunks can be partitioned across those nodes. So with hypertables, we get faster inserts and queries because of this time constraint. We know that we only have to write at the end. So that allows the query optimizer to speed certain things up. Indexes get faster. We get age-based data compression and reordering features. And what's really cool about the chunk-based architecture is that your data set can usually fit in memory because you're typically querying the last n number of days or months or years. And so you could design your chunks so that they're always pulling in and sitting right in memory. So this is what a hypertable might look like. We're writing data, and as this data is written into the database, on a normal table, you would just see rows, but instead we're assigned chunks, and these chunks have a timestamp and then their value and other columns. We've decided to chunk by days, so hopefully you can see that that first chunk is on January 2nd, and then January 3rd, January 4th, and they're all split out. Now, something worth noting is that you want to have your chunks being able to fit in memory, but you also don't want to create them too small because you're going to add some amount of overhead with these chunks. And so tuning your database to have your chunks be about the right size is really important. And there's a ton of documentation for how to make these determinations. Now, Timescale ships with something called a hyperfunction, which is a SQL extension. You're going to get functions like time bucket, first and last, histogram, and dozens of other really interesting features. And this makes data analysis easy. So I think a typical pattern might be you're going to query data. Sorry, if you're not using Timescale, you'll query a bunch of data. You'll shove it into something like, I don't know, pandas, some data frame library, and you'll do all of your data analysis inside the application code. With the extensions that you get with Timescale, it makes it so that you could do a lot of these aggregations all inside of the database. And the best part of it is it's just SQL, so it's going to work with your existing tooling across pretty much every language because you're using SQL across every language. OK, let's get into some real code now so that we can see kind of what we can do with this thing. So this is going to be a really simple example, but from the heartbeats table we've created before, again, it's just got a timestamp, and it belongs to a user. I'm going to pick me, and we're going to query all of my heartbeats in the data set, and we're going to get the first and the last. And what you should see on the bottom there is that we've got the beginning of the day of October 27th and the end of the day for October 27th. That's because I generated a full day's worth of heartbeats for that. So you could see in the select there that it's calling first and last on the timestamp. And it's a little bit weird because you're seeing timestamp twice. But you always, in the second argument, have to give that time partitioning field that we easily name timestamp. But if you can imagine you're grabbing something else like the last workout of the month, you'd be first passing workout and then the timestamp. OK, so we got this giant query plan right here. To get the first and last rows, Timescale is actually going to change the way that Postgres works with the query planner, and it's going to use special indices to pull data out faster. So I generated an application with 5 million rows, and I was able to pull out the first and last of that data set in about, I think, 25 milliseconds. And it used this chunk append custom scan, where it's going to be able to eliminate entire chunks of data because it can see that first and last time constraint on the chunk. And again, this is kind of like what enables all the interesting features. So you could also see on the bottom there, it did an index scan on the chunk that it found where the last value is going to be in, or possibly the first. And the other thing, just going back to this, so you probably can't see, but there's 2 query plans here. So it ran one for the first and one for the last. If you imagine doing this in regular SQL, you're probably going to do something like a order by with a limit 1 to grab the first, and then swap it from ascending to descending to get the last. And that could be pretty fast if you're doing an index on that column. However, once you start to add a lot of other attributes and you want to do fancy aggregations where you're looking at a bunch of fields, you're going to have a lot of indices, which adds a lot of other complications. So being able to do this in one query and have Timescale take it, optimize it for you under the hood is very powerful. OK, now time bucket is kind of like the bread and butter when you're going to want to start working with TimescaleDB. And you can think of it as a floor function for timestamps. So what is math.floor? It takes a decimal value and it chops off the decimal part so that you get the bottom integer. Time bucket kind of works exactly the same way, where it takes a timestamp and it's going to clamp it to whatever interval you say. And then you can use interval math to move it around that origin. So if you wanted to time bucket things for not every minute, but every minute and a half, you could time bucket on the minute and then add 30 seconds to it. So this is what time bucket looks like. We're gonna query from our heartbeats. We're gonna get the timestamp, and then alongside it, we're gonna see what a 1-second time bucket looks like. So we can see on the left, we've got heartbeats. They're being generated every few milliseconds. So we've got microsecond precision on our timestamps. And then on the right, we've time bucketed these into the nearest second below our timestamp. Now, we did this for 1 second. You could do it for 2 seconds, 5 minutes, 3 days, 1 month. It's extremely flexible. OK, so now let's do something interesting. Let's calculate our beats per minute from our example earlier. So we saw the hearts going across the page. We want to start at the beginning of a minute and the end of a minute and just sum up the number of heartbeats that we saw. So with this, we're going to group by the minute. The minute is defined as taking the 1 minute timestamp and calling that minute. And then we're just going to sum up the number of heartbeats and call that our beats per minute on line 7. And just like that, we've got roughly around 115 beats in each of these minutes, with some variance there. And each of these time buckets are exactly on the minute. OK, not every application is going to have 100% uptime. We all know that we measure our availability in nines. You're going to miss data. And when our systems miss data, that creates all sorts of complications for reporting. It causes complications because your users are probably upset. Timescale provides utilities for working with filling in the gaps in data like this. So we've got 4 days here, and the third day is missing. What do we do about it? So first things first, we can use what's called the time bucket gap fill function. So just like we saw with the time bucket before, time bucket gap fill is pretty cool in that it looks at the where clause of your query, and it has to be like a group by aggregation query. But it looks at the where clause, and it uses that to determine the start and ending time. And then as it returns the time series, any time buckets that are missing, again, you've chosen an interval like 1 second or 1 minute, it's going to fill in those buckets. So we could use time bucket gap fill in this example to say, I want all the data from November 1st to November 4th, and with time bucket gap fill, it's going to fill in that timestamp. OK, that's fine, but what about like the data? Like I'm missing data. What do I do about that? Well, we've got 2 functions we could work with. One is called last observation carried forward, which does exactly what it sounds. It takes the timestamp before, and it grabs that value, and it assigns it to the next. You might call this imputing in some contexts. The second is interpolation, where it will linearly interpolate between 2 values. So if you have like 5 and 6, it's going to choose the value as 5.5 for in between. Now, you have to be careful, obviously, when you're using features like this. If you're generating data that is not real, context matters, so be careful. But it is a very powerful tool. OK, so let's look at an example of using this gap filling measure. So we're going to query from the heartbeats again. But now we're going to call time bucket gap fill with 1 second instead of the regular time bucket. So this is doing exactly what we saw before, but we're also going to put in that where clause. We're going to say from 9 o'clock in the morning on November 1st to 9 o'clock and 5 seconds, want to get all of the data in between there. And as you can see, it's giving us all of the data back. We've got all these users, and these timestamps are filled in. Now, with last observation carried forward, if you're missing data, so we see this value column, and anytime that it's blank, it's missing data, what it's going to do, last observation carried forward, it's going to take the last observation, so the second line of data, it's grabbing 5, and then it's going to place that in for the next one. It carries 7 forward in that second example. And this is obviously a really interesting, powerful tool here. OK, interpolate works exactly like I said before. So instead of the last observation, it's going to see the gap. So we've got 5, we've got 7. It's going to linearly interpolate 6 in between. Or if you're between 7 and 8, it will linearly interpolate 7.5. All right, so cool, we could query data. What about, I've got a ton of data. I'm generating heartbeats across dozens. My app's really popular, thousands or tens of thousands of users. This data gets really big really fast because we're going to be capturing a lot more than just that. So we can introduce compression policies. And we say on a table, I want to segment the table by a particular attribute, so user, and I want to compress the table based on that. And the compression policy, you say after what time period Timescale should start compressing the data. So in our case, we're going to say after 7 days, start compressing the table and make it smaller. So what happens to the table? We have our row-oriented data where we've got users, we've got timestamps. When you compress the chunk, right, because we're compressing chunks, not tables, it flattens it into an array value. So it becomes a single row, and each of the values are going to be at the same index in these arrays. Now, with this and some other really interesting features that they have, you can get up to 96% compression on your data. So it's using things like gorilla compression for floats, which I have no idea what that means, but it sounds really cool. Delta of delta, simple 8B, run length encoding. Some of these things are coming back to me from my computer science education and Huffman encoding, but it uses a number of different state-of-the-art compression technologies to bring the size of the data down. If you're seeing a repeated value over and over and over, that's where something like run length encoding comes in, where I could just say value, number of times we see it, and boom. Now, compression doesn't come for free. Some of the challenges you might experience when working with compressed data, once it's compressed, it's hard to change. Actually, in fact, you can't necessarily change or delete the data without deleting or changing the entire chunk. The database migrations are going to increase in complexity because you can't migrate fields on chunks that are compressed. But you can always decompress, so there's always an escape hash. This is not permanent. So you can iterate over all of your chunks and call decompress on them one by one. This can take a while if your data set is very large. You can then remove the compression policy, disable compression, and then migrate your table. OK, let's get into more interesting features, continuous aggregates. So we've got large amounts of data. We want to run interesting aggregations on the data. Those aggregations are going to get super slow as we've got millions, billions, trillions of rows. So continuous aggregates help us solve this problem. They're basically materialized views that have triggers and some other interesting things happening in the background. And what happens is when you insert data into the hypertable, it's going to automatically refresh that materialized view, and you get this live aggregate that you can work with. So let's take an example of calculating the minimum and maximum beats per minute for every user. So I'm going to create a new materialized view called heartbeats minutely with TimescaleDB continuous, which makes it this continuous aggregate. And then I just write my function my SQL query as I would have. So bucketing by minute, counting up the beats in that minute with the user, grouping by the user. Now, from this, we can query heartbeats minutely, this materialized view, directly. So now I'm going to calculate the min and the max, again, time bucketing by the day. And I'm going to group by the user in the day. And now I've got the minimum and maximum beats per minute for every user for each day. OK, we got compression. We can aggregate. We want to get rid of data, too. So time series data, we know can get large over time. What we could do is we could set retention policies on our hypertables and say, after a year, ditch the chunks. I don't care about it anymore. What's super interesting is that you can configure your continuous aggregate so that it can continue to contain deleted data. So I might care about what my average beats per minute on a daily basis was 5 years ago, but I don't need the individual heartbeats. And these two things in combination help solve that problem. So I get that summary data without all of the individual data points. Best of both worlds. As a bonus, TimescaleDB also can work as a backend to Grafana and something to really replace Prometheus. I don't know about you, but if you've ever written any PromQL, it's not my favorite query language. So now you've got SQL, you could query, you could pump in your application metrics and use Timescale to power your application observability. All right, so let's recap. TimescaleDB, it's just Postgres. We get automatically time partition tables using chunks on hypertables. We get all these amazing compression features. We have advanced time series SQL upgrades and continuous and real-time aggregates. And it's just the SQL you're familiar with and use probably on a daily basis. What we didn't cover is replication and backups. It's got a number of different solutions for that. Distributed hypertables, you could distribute your hypertables across nodes for really large data sets and not have to store it on every node. For things like continuous aggregates, they have a user-defined job framework that runs behind the scenes that you have access to, and dozens upon dozens of hyperfunctions that we did not go over. Now, I love Elixir for many reasons. One of my favorite reasons is the quality of documentation and the ubiquity of it. Postgres also has a reputation for great documentation, and I think Timescale takes it to a next level. So if my talk at all interests you in that, the docs are going to be your best friend. Now, there's plenty of other alternatives for time series data. QuestDB, Prometheus is one just mentioned, Open Time Series Database, probably a bunch that I haven't even mentioned. The one that I think only comes close to TimescaleDB in terms of its accessibility is Citus, because it's also a Postgres extension. But I think the real value of TimescaleDB is that you have your existing Postgres, you upgrade with this extension, and you get all these really nice features. All right, so spoiler alert, we've been looking at Elixir code this whole time. How could that be? Because we have a Elixir library that works with Ecto for Timescale. So it extends the Ecto DSL. It's basically just a thin wrapper around the fragment macro and some other things that we may have stolen from the Ecto code base. It has features for database migrations, hyperfunctions, actually doesn't have any continuous aggregate features, and would love to have some, so call for speakers. Would love for you to get involved. We provide native documentation, and best of all, this entire talk is available as a live book that you can interactively go through these examples and play with it. So it's currently in alpha, but I'm using it in production at my company Bitfo, so it's working really well. And yeah, just to recap what it looks like, it is what you're familiar with your Ecto queries that you use every day. Actually, and I should mention, especially with Andrea talking earlier about working across the ecosystem, TimescaleDB, any database driver, you're going to be able to use it because it's just SQL, so you could pass strings and you'll be fine in Erlang, Gleam, or any other Beam language. So yeah, go check out, if you go to the documentation on Hex, and you can click guides, you could run the whole thing in Livebook. There's even a section for how to install Timescale on your machine. And we have a bunch of open issues. We are in alpha. There's a lot of things that are still missing, but we'd love to get you involved. I think it's a great opportunity, a very accessible way to get involved in open source. So please get involved. And thank you to the Timescale team for providing amazing documentation that I stole most of this talk from. Peter Ulrich, who reviewed my presentation, and Timescale Elixir contributors, and my workplace, Bitfo. So thank you very much, everybody.
Thank you, Dave. All right, we do indeed have time for questions. I also just want to shout out before we do that we have a slight schedule change because the talks in the other room experienced some technical difficulties and got started a little bit later. We're going to break for lunch after this talk, and the talk that was meant to be after this is going to be right after lunch, just to let you guys know. All right, so I'm going to start off with a question from one of our virtual attendees. I think you touched a little bit on this just now, but is there an ORM that you use or recommend as the best fit for working with Timescale and Erlang?
I actually tried searching for what people typically use as an ORM in Erlang, and I don't know. I didn't find any really good answers. I found a bunch of database drivers, so I don't have any recommendations, but I'm curious if someone else does.
Cool, thank you. We've got some questions in the room. We're going to start with Ian.
Hey, so first, great talk. Second, I guess I'm curious, right? So you said you just run this as an extension in Postgres, but you also said you're using managed Timescale. Do you run your normal operational workloads inside of that same database, or do you have your user database and your Timescale database? How are you architecting that?
Right. So one database, relational data, time series data. So in my domain, I work with financial data. I get price ticks that I'm collecting maybe every second. So I use TimescaleDB for that, and then for any symbols, we join in relational data, so more information about the symbol. So the real value is that they all get to live alongside each other.
Yeah, cool.
So yeah, one database.
Awesome.
Can you throw up the hex docs link again? Can we have that be the page there? All right, and in the meantime, we've got a question from Lucas.
Hello. Also, nice talk.
Thank you.
We liked it. And I would like to know if, like, when you create a new table for the chunks, does it duplicate the data, or it saves like a reference to the original table to save the data?
Right, so the table doesn't change. It's like if you were to create the table and then make it a hypertable, there is other, let's call them meta tables. I don't know the correct vernacular, but Timescale is keeping kind of bookkeeping about, what are the hypertables, what are the configurations of them, all these different attributes, and then it's working kind of in the back end of Postgres to change the query plan for it. Whenever a row is inserted, it's going to insert it into a chunk rather than the normal table architecture. So it's transparent but opaque to you. You just write data as you normally would, and then all of this exists behind the scenes. There's no duplication of data. It's just one table.
Oh, cool. Thank you.
Any other questions from folks in the room? We've got a few. We're going to start over here, and then we'll make our way over there.
Thank you. Thanks for the talk.
Thank you.
Can Timescale rescale? So if you have, for instance, asynchronous from two sources and they're not exactly synchronized, you can use Timescale to resynchronize on a second-by-second basis?
Let me see if I understand your question. So you have, is it like two nodes and you're trying to sync across two nodes, or?
Well, suppose you have data that comes out at random times, but you'd like to match it with something, process it with something that comes out every second. So you want to resample the random time data for what it would be at the
Got it.
at the second by second.
Okay, yeah, so you have data coming in. It's maybe coming in, within a 1 second window. Every so many milliseconds, microseconds, you're getting data. So there are functions for downsampling. There's features for, we saw the time bucket features, but there's features as you insert so that it can sort of decide what chunk it goes into, or if you want to manipulate the data in that way. But if you're writing data outside of that time partition, it doesn't really matter, because you're just going based on the chunk configuration. So if it's still inside of the end time window for that chunk, it's just going to fit into that chunk. And then you could deal with any of that other complications on the query end of it.
We've got another question online, and then I'll hand it back to the folks in the room.
Oh, there's a British man in the back who had a question.
Well, he's going to wait because I'm going to read the one online first. Running TimescaleDB in multi-node means also Postgres should be running in multi-node env, question mark?
Well, okay, so Timescale is not a different process. It's all running together. Running Timescale multi-node. Yeah, you're just running multi-node Postgres. So it's no different, and it comes with all of the complications of regular multi-node Postgres. So good luck.
Hi, Dave. Great talk.
Hi, Chris.
My question was very related to that one. So how does it work with sharding out of the box? And does Timescale give you any kind of tools to help with sharding Postgres?
Right, so maybe you want to have a partition key because you're writing to different, you got different customers. And maybe you're like building a notification system, and you want your notifications written to different shards, something like that. I don't know if you're familiar with that example. Yeah, there are plenty of features that work, just like with regular Postgres sharding. It works harmoniously with that. So I don't have any specific answers for you, but we could talk later.
All right, we got another question.
Hey.
Hi, Desmond.
What happens if I want to change my chunk size? Let's say I start at 7 days, and then I decide I want it to be 3 days. I assume that I can do this, but how much of a pain is it?
So yes, you can change your chunk size. There are certain things that are hard to change after you've configured them, like compression. If I've compressed the chunk already, I have to uncompress. The chunk size, the chunks are getting written over time, right? So if you change the chunk interval, which is the amount of time that data gets grouped into a chunk, you could change that on the fly, and it won't matter. It'll just continue.
It won't go back to the previously written chunks and rewrite those?
The chunks that are already have been written will stay in that same chunk size. You can reorder and rechunk the data. I don't know, maybe that's what you're asking. You could do that too. It's just a little bit more operationally painful, but possible.
Any other questions? All the way on the other side of the room. This is actually good because I'm so cold, so it's helping me to warm up a little. Yep. You go, sir.
Thank you very much. Awesome talk. Thank you very much. I learned
Thank you.
lots. Question I wanted to ask on this is, although I can see the advantage of timescale when you're looking at multiple different issues within a certain time set, if instead you're looking at a system where you could be querying individual rows of any point in time in the entire history of your application, is there an advantage of using timescale over something as simple as even a KV store, for example?
Good question. If you're trying to look up things by individual rows, and yeah, if you have something like a key value store type data set, you probably don't want to work with TimescaleDB because you're not really dealing with time-oriented data. If you kind of have both, where there's time-oriented data, time series data that you're working with, and application data that you want to, they need to be joined together in some way, but they're fundamentally separate. You can have them as separate tables, and even in my example where I had my time series had a user ID on it, I could just simply join in the user onto the time series or vice versa. So you have that flexibility where if you need to do primary key lookup type stuff, those like a different type of workload like that, they can coexist and you could bring them together.